So what we're going to do today is the boat float experiment. It's an experiment where we are exploring Archimedes' principle. So now that we've had Archimedes' principle all of yesterday, remind me, what is Archimedes' principle all about? It's about buoyancy, and specifically that the buoyant force is equal to the weight of the fluid displaced. So everything we're going to be doing today is going to be looking at that relationship, see how it works. So we've got the things laid out in front of you. All of the theory is, well, all of the theory. There's no theory here. The theory is this right here. Not a lot of theory. So getting right to the procedure, it says use a spring scale. Instead of the spring scale, we're going to use these. So I'm going to show you how to use those so you can use them effectively. You can see that there are, well, 3 stations set up, and then I took the 4th one here. So to do that, you need to go to the Capstone software and open, of course, the appropriate experiment. And I haven't plugged mine in yet. I was like, what's wrong? It needs to be plugged into the computer. Fortunately for you, yours are already plugged in. Fortunately for me, once I get it plugged in, it just recognizes it. Okay, so now I have things so it can read it. This here is a force sensor. It has a very important button that says tare. Tare means to reset to 0. Right there. It says 0 actually on these. The older one said tare. So we are going to use these to measure the weight. Now, we can go through a calibration process that we use, additional weights for. I think that these things are close enough to calibrate that we can trust them without doing that. So to make a measurement, I will just, okay, you guys have used this software last week, right? So you have some familiarity. I'm going to tell it to record. And now it's recording data and it's saying how much force this is measuring. 54 newtons is a lot. I pressed the 0 button and it changed to 0. See how that works, right? Now I'm going to put something on there to weigh. Unfortunately, most of my normal things that I would weigh are put away. I used to have a bunch of weights that I just kept here, and I was like, that's just cluttering up my desk. And I put them all away. They're supposed to be in these cupboards, but I don't think they're there either. Alex left the door open. It's easy to get to. Okay, so here's a set of masses. And I'm going to put a mass on there just to see what it measures. So this one is 100 grams. How much does a 100 gram mass weigh? In newtons, by the way. Okay, we have to multiply it by 9.8 meters per second squared. 100 grams is 0.1 kilogram. So 0.1 times 9.8 is 0.98 newtons. So it's virtually 1. So I put it on there. Looks just right. Pretty easy to measure with this, right? So you're going to be using this to measure the weights of things. Anyone have questions about how it's measuring? How to set it up? Pretty straightforward. Has to be one way or the other. Okay. One person nodded, so I'm going to assume that she speaks for all, that you understand this. So back to what we're going to do. The first step in the experiment is to weigh your object out of water. So I just hung it on there to weigh it out of water. But I'm going to need to weigh it in water, right? So what am I going to do? Well, I really need to, where'd I put the string? I took it out and set it somewhere. Right here. I need to use string so I can lower it down into water. So I'll just cut myself a piece of string and tie knots on it. And of course, when I was a kid, My dad tried to start a Pathfinder club, but the church said we don't have enough money. And so I didn't have Pathfinders, and hence I have a great excuse for not being a great knot tire. Because back in the day, everybody learned to tie knots in Pathfinders. These days, I'm not so sure, but no, I say that because I spent all day Sunday teaching the optics honor to Pathfinders, but the students only had 2 hours of learning. How is she actually going to learn in 2 hours? Virtually nothing. And you're supposed to do all these things. There's no way to do all the things in 2 hours. So I put that on there, and I get my weight in air is let's say 0.987 newtons. Now I'm going to weigh it in water. And this part here, you'll want to do the two things in series. You have two parts there. The first one's going to be weighing it, and the second one is going to be determining how much water it displaces. So since I gave you one, Ashton, I don't want to keep going back and forth. I'm going to take it away from you. I'll read it back first. So I want to measure the volume of water displaced. So I'm going to start by taking this and setting it here and measuring very carefully what the water is. Now these are graduate cylinders. They're made to measure the volume. And you look at this and you want to sight so that your eye is looking along the bottom of the water that's at the top, right? The water at the top has what we call a meniscus. It goes like this. And you just want to measure the height of the flat part. Things to keep in mind are this has 10 marks between 450 and 500. So each mark on here is 5 milliliters. So 5 times 5 is 25 and so on. So right now it's there's 350, 375, 380, 385, just under 390, so I'd say 388. So you'll want to write down in the line that says volume of water displaced, leave a little space and write 388 milliliters. Leave a little space because you're going to put another number in front of that after we do the second part.
What was that number?
Well, this is for me. You're going to have different numbers. But you want to write down what the volume is before you put it in. And then I'm going to leave that in place and bring this over so I can put this down in here so that's completely submerged and have my balance up above it. So I want my mass in there, not touching the sides, just freely hanging. There, that fits the bill. Now we have the new weight. Did the weight go up or down? Down. So that's what you're having in the second item here, the weight of the object in water. So for step one, the second line, right, the first line I had 0.988 newtons, and now I have 0.809 newtons, or 810. With that fluctuation, you have to choose what you think is the best. The reason I have the graph is because you can go to the graph and choose a segment and find the average, and that would probably be your best estimate. So I have that number, and then I have this one. So this one here, it's now reading right at 405. So on the second line, remember I said, I would write 388 milliliters, but I left a little space, and I put 405 milliliters minus the 388 milliliters, and that gives me how much water was displaced by my mass. And I have the water displaced is step 2A, so you just continue that subtraction to get your answer. And then the mass of the water displaced, well, how do we go from volume to mass? What's the physical quantity that relates volume and mass? The thing that is the mass per volume. The density. So the density of water is the mass per volume. We have the volume, so if we multiply the volume by the density, that will tell us the mass. Well, the density of water is 1 gram per centimeter cubed. That's what we said in class. A centimeter cubed is the same as a milliliter. So it's 1 gram per milliliter. So this number here was measured in milliliters. For my case, I said it was at 405, right? Yeah. So for my case, I had 17 milliliters of water displaced. Multiply 17 milliliters by 1 gram per milliliter. I have 17 grams. It's the water, the mass of water displaced. And then the final line here in step 2 is the weight of the water displaced. So what's the weight of the water displaced? Well, we have the mass. How do you go from mass to weight?
You
Multiply it by 9.8. Once again, remember that you need to convert it to kilograms to get it in newtons. So my mass here was 17 grams. Yeah. So I'd have 0.017 times 9.8 to get how many newtons it was. Then we turn over to the back page, and how does the buoyant force of the submerged object compare, with the weight of the water displaced? So that's just going to be comparing what you had here for the final line in step 1 with the final line you had in step 2. Now for step 3, step 3, step 4, and step 6, you're going to be making measurements and putting the measurements in this data table here. And then you're answering questions in the steps. So step 3, and actually, I can give this back to you and go away from the this because we don't need to be doing this anymore. So now it tells us here to use a balance to measure the mass of a piece of wood and record this mass in the data table. So we're going to give you some wood cylinders. Each group will have one wood cylinder, and you're just going to use the triple B balance. You have to bring it out, set it down, zero it, and measure the mass. And then you're going to repeat your measurements. Essentially, you're going to measure the mass, measure the volume of water it displaces when it floats, and record those in your data table. So for the wood, you're going to put the mass that you measured on your triple beam balance here, the volume of the water displaced, and then how do you go from the volume of the water displaced to the mass of the water displaced? You multiply by, convert it to kilograms. Actually, no, this is not. You just multiply by 1 gram per milliliter. So what can you tell me about the numbers that are in these two boxes? If you multiply by 1 to go from one to the other, they're going to be the same. Okay, I want to make sure that's clear. The reason we have the two different boxes is because they're two fundamentally different things. But because water has a density of 1, the volume displaced and the mass of that displaced is going to be the same. So you're filling that in. Now that says wood plus 50 gram mass, we're just going to go ahead and skip that. So you're not going to do the wood and the 50 gram mass. That's step 4. So you're not going to do this one here. But then for step 5, you're going to use Play-Doh rolled up in a ball. So this is step 5, step 3. We're skipping step 4. And then step 6 is Play-Doh again, but with it in the shape of a cup. Now, the Play-Doh, get myself some Play-Doh here. To do the Play-Doh, I get myself some. For the first part, I roll it up in a ball. I want to be able to, even though it's going to sink, so I'm going to have this so it sinks to the bottom. I'm not measuring how much it weighs, but I do want to maybe get it out without dumping everything. So I will put a piece of string in this. How do I do that? Well, it doesn't take a real lot of thought because it's Play-Doh. So to get the Play-Doh out, I'm going to take the Play-Doh, put the string in here, squish it all about the string. That way I'll have something that I can pull it out with. Of course, my string's not long enough because you just need to, well, you're supposed to just put it in there and let it sit on the bottom. Right, I can't quite do it right. I have to keep my fingers here. But if I made my string 4 inches longer, I'd be fine. And then I can bring it back out. So that's what you're doing for step 5. For step 6, it's all gooey when it gets wet. For step 6, you're going to take that same Play-Doh and you're going to form it into a vessel, a hollow vessel that will then float. That's what you're doing when you have a boat. You're making a hollow vessel out of material that's more dense than the water, but by giving it a cavity inside, it's going to displace a water that weighs more than this, even though it's less dense. Now, once again, I'm going to want to get this out, so I will find a way to make my string incorporated in my vessel here. And so now if I did it right, it should float. Didn't do it right. Also didn't make it stick well. Now what do I have to do? Dump it all out. So do try to make sure you make it stick in there well. And it will take, yeah, thanks. It will take a few tries maybe. As you see, I thought I had something that would float and it didn't float. Needed to make it taller and skinnier. Notice I just made it on my finger. You do want to make sure that you don't have holes in there. I just told her it's great. You see that it is a little water soluble. The water can be cloudy. So try not to leave it in the water too long. Maybe don't use brown either. It just doesn't work. Think of it like a chocolate bar, okay? Think of it like a chocolate bar. So we've got Dr. McNeil's Play-Doh up here for you to play with. Yeah. Give me a sec. Yeah, that's nasty. And we do have things to dry our hands on all over the place. But yeah, they used to be very, very good about putting them out here, and I was very, very good about moving it. So we now have lots of these things, like they're in the cupboards and stuff. So they're not sitting out anymore, but they're in the cupboards because they just kept putting it here, and I kept putting it in the cupboards. All right. Then we have a bunch of questions to sum up what you've done. And then we have going further. Now, the going further has you start with a prediction. And then it says, float a toy boat loaded with lead cargo. What I'm going to do is I'm going to bring out a basin and a pie tin and some masses. And we're going to put some mass in the pie tin to do that. And so that, we'll just do it once with everybody. So we'll do all of those measurements together when you guys are, when the first group is done, we'll do it, okay? That way we have a time when we're not going to make anybody wait, but you can get at least most of it done before we get there. So we're going to do the stuff in this backside and the actual experiments and right here. And then you're answering these questions here based on what we did. So yeah. This one here we're not doing either, so not doing that. Actually, I think I skipped 8 as well. What was that?
9?
Or 9, yeah, the one I crossed out.
So we're not doing 9 or 10.
Yeah, so not 9 or 10.